Welcome to Planet Geo, the podcast where we talk about our amazing planet, how it works, and why it matters to you.
What is the cold intro, Dr. Remick?
It's a cold open. It's a cold open.
Sorry.
I've got something for it, Chris. I was this afternoon. I knew we were sitting down to record, so this afternoon I really started giggling. And do you know why I was giggling to myself? Can you hazard a guess?
I have no idea why. It's been a good few days, but I don't know why you'd be giggling.
I was giggling to myself because a couple days ago I called you and I had a little bit of what I thought was cranky Chris on the phone. so about 15 minutes into the call, I was like, dude, are you a little cranky tonight? And you go, no, I ate too much at dinner and I'm just upset and uncomfortable. I was dying. You were just like, no, I'm not cranky. I'm just uncomfortable.
I ate too much. I felt bloated, and I don't like that. It's a horrible feeling. But Jesse, I love food. It's just anybody that knows me knows I love food so much. And I made something really good, and it was a spicy sausage lentil soup.
Oh, that sounds good.
It was good, and it was I had a bowl of it, right? And I'm like, oh man, I ate it really fast, and that's the mistake.
That's the mistake.
And then I went back, and I'm like, well, I'm still kind of hungry, so
you made yourself
filled another
bowl.
one up and went. Wow, oh, I demolished it. Yeah, it was not a good life decision right there.
No, that's right.
Not a. Yeah, well, So Jesse, come on now. You don't cranky Chris. Is he really a thing?
Yeah, I mean,
I get cranky Jesse every now and then.
Let's get Jenny on. Let's get Jenny. Bring Jenny down here and let's ask her if cranky Chris is a thing or not. Every once in a while, or I don't know if cranky. You're not. I get worked up, Chris. Sometimes.
Yeah, you do.
You're rarely like
Absolutely.
low.
That's a thing.
That's fair. You're rarely like low. You're like either worked up in a positive way or let's say a negative way.
Yes, I do allow myself. I was going to say luxury, but it's not really luxury. I do get worked up.
Yeah, and that's fine.
I happens. Yeah, so
I mean, everybody
you get
does,
emotional,
right?
Chris. Sometimes.
Yeah. That's right. It's just depending, is it the positive emotions or the negative emotions? But I'm pretty sure looking at you, I got the positive emotion, Chris, on the line right now.
You do. You have the positive, Chris, because Jesse, today. Oh, this is exciting. Today, our topic is about a paper that you wrote. You co-wrote, okay?
Yeah, co-authored. Yep.
And co-authored. I'm sorry, I'm not using proper terminology there for Dr. Remick.
The doctor is in the house for this episode.
Yeah, and I'm going to apologize to all of our listeners outright for that. But we're going to talk about this paper, Jesse, because this was, let me ask you, where is this going to be published?
Yeah, so this is published in Nature, which is the big dog, I guess. I mean, this
that's
is the big
the top
one,
tier,
right?
That's a big. Wow, that's a big deal.
When you think of scientific publications, Nature and Science are they're really the oldest ones. They're short papers. They're interdisciplinary. You know, there are good and bad papers published in Nature and Science all the time, but it is nice to get published in Nature. It means it's sort of a topic. You're writing a paper on a topic that is important to a wide range of fields. So, Chris, one other note though. It's been a good couple months, I'll be honest. We had this Nature paper accepted that we'll talk about, but we also found out recently that our Yellowstone National Park audiobook is going to be available in the bookstores in Yellowstone National Park. We're partnering with Yellowstone Forever to have them displayed in Yellowstone National Park and sort of been approved by the National Park Service. And so that's a really exciting development for us on the Camp Geo app.
That was not enthusiastic enough, Jesse, because
I know.
That is so
fun.
Awesome. I've been on cloud 9 for the last 3 days.
Yeah, it's been great. We've had a good little run here. Yeah, we've had a good little run, and we're just super excited. Yellowstone Forever is going to partner with us on this, and it's great. Super excited about this.
Okay, Jesse, can we get down to this a minute? So the title of your co-authored paper
hold on. I'm putting on my emotional armor right now because I get the sense I'm going to get a lot of crap here this episode.
Well,
and most
so I don't know. Yeah, you might, but I do have to be careful because you did co-author it, and I don't want to offend your co-author in the least bit. I maybe only want to offend you a little bit.
Professor
but that's
Andy
just in good jest
Smy is
because
quite hard to offend, so don't worry about it.
Okay, that's good to know. That's good to know. All right, Jesse. So the title of your paper. All right, Jesse. This paper then is released in Nature.
That's right.
Right now, as we release this episode, this is a paper that is out.
Yeah, that's right. And we'll put a link in the show notes here. And this is we made it open access, like we paid for it to be totally open access, so you don't have to. It's not behind a paywall at all.
I hate that when I don't get open access to those.
I know. So this one's open access.
Okay, awesome. So the title of the paper, Jesse, is everybody ready?
Here we go.
It is called Subaerial Weathering Drove Stabilization of Continents. Okay.
And
Jesse.
Everybody goes wild, and the crowd goes wild.
It's crazy. Okay, let me read it again just for impact. Subaerial weathering drove stabilization of continents.
So I have a question for you, Chris.
Can we talk about this a minute? Okay, go ahead.
I mean, what do you, the first time you read that, what were your thoughts? What was your knee jerk? What was your gut, reaction? Because this is something we agonize over, right? Like as writing these things, we're like, what should we put the title as? And I'm not sure we got it right? We had a whole bunch of options we were picking from, but what is your reaction?
Can I answer your question with another question then, which is, why is this an important question to answer?
Oh, yeah. Okay. We probably need to do a bit of Archean geology background here a little bit to kind of understand this. But the tagline, the short tagline, and we've talked about this before, continents are, as far as we know, singular to the planet Earth and really a major feature of what makes Earth unique. And it's intimately linked to oceans. We've talked about that before. So understanding the continents is a really important thing to understand when we compare our planet to other planetary bodies.
Yeah, because when you compare us to the other terrestrial planets in our solar system, Mercury, Venus, Mars, they don't have continents in the way that we do. They don't have tectonics the way we do.
That's right. And so you kind of ask yourself, why are continents stable? Why are they stable for billions of years? And, there's some first order things we know about them, but it's also a bit of an open question.
Okay, so are you saying then, let me re-ask I don't know if I want to re-ask the question, but are you saying that the purpose of this paper then is to answer the question about why Earth is unique?
Kind of, yes. I mean, it's certainly intimately related to that topic. Why is Earth a unique planet? Why is Earth different from Venus?
Don't you think you need help with title work then, Jesse?
Okay, so there's an answer to my question.
I don't know. I think I came up with maybe a more interesting, I don't know. I would not have gotten what you said, which by the way, I want to be really clear on this. I think that answering the question about what makes Earth and Earth's continents so unique is really, really important. And I think very interesting, but I would not have gotten that out of that title.
No. So it's a difficult thing, right? Because
is it a nuance?
Well, there's some nuance to it because we submit this paper, it goes out to other people like us, other experts in Archean geology or in granite formation who look at this and review it. So if you put a really catchy title that's attractive to the biologists in there, some of the reviewers might be like, that's a stupid title. So you have to toe this line between scientifically accurate and rigorous and catchy. And that's, I mean, I'm not saying I'm great at it. I'm not good at episode titles. I'm not good at paper titles. So
this.
There's people who are better at this, but it is a hard one, I think, for most people.
That's a really interesting comment. I find that amazing because I think that this title hides what you're really trying to do.
I think that's probably right. Yep, I would agree with that. It is a little bit too scientific, maybe.
Okay.
Or it could be simplified and made more powerful.
So if I go back to, and I think everybody, if you did not listen to our episode on how to read a scientific paper,
ooh, that was a fun one, Chris. That was a fun one. It was fun. Like a year ago,
and we got some really
summer.
Good responses, online about that. We got good emails about it. Go back and listen to that episode if you haven't, or it's been a long time, and then maybe listen to this, or maybe sit down for an hour and slug it out with this article that Jesse and his co-author wrote. But can I read the first sentence?
Yeah.
Okay. Well,
Get the armor on.
So
yeah,
again, the title is Subaerial Weathering Drove Stabilization of Continents. And the summary paragraph intro sentence is Earth's silica-rich continental crust is unique among the terrestrial planets and is critical for planetary habitability. That one sentence is the title to me. And I think it's an awesome title. I think it's catchy, and I think it's intellectual enough for the circles you run in.
I totally agree. I love that intro sentence. I'm glad you liked it too.
I do.
That
Absolutely.
part introduces why this is an important topic. Why should we as a field, why are there thousands of people working to understand the history of the continents? That sentence is kind of a summary of that. What it doesn't do is it doesn't summarize our proposal or summarize the new features of what we're suggesting here.
All right, let's get into that in a minute. So I'm going to have you set the stage for this, because you then go into very quickly into cratons, and I'm going to have you introduce to our listeners, because some of them I'm sure know what a craton is, and I'm sure some of them do not. So what is a craton, and why is that an important aspect of your discussion?
What they are, first of all, is cratons are big blocks of continental crust that have a thick mantle keel beneath them that are stable.
Mantle what?
Mantle keel. Like mantle keel, like a boat's keel underneath of it. You know, like a sailboat has this big keel. We refer to them as keels because we think of them as stabilizing the mantle root, the mantle lithosphere. So this is part of the tectonic plate. It's really thick. It's 250 kilometers thick, and it helps make sure that that continental bit above it, the continental raft at the top, is stable for billions of years as it gets batted around the Earth by plate tectonics.
Interesting. So can we talk a minute then about how does that...
Chris, I missed out one key point. It's stable, meaning like not much has happened to it. Hardly anything. If we go up to the North American craton, the Canadian Shield is kind of another term for what we think of the North American craton. If you go up to the Canadian Shield, you're walking across 2.5 billion-year-old granites that look exactly the same as the granites in Yosemite National Park that we talked about with Mike Ackerson that are 90 million years old. And literally nothing has happened to them. They've been right near the surface of the Earth for that long. That's just like a tectonically stable tract of crust that has just, think of it like an iceberg being blown around the ocean, and it kind of bumps into other stuff, but it doesn't actually do anything. It just sits there.
I have so many questions based on what you just said now that I want to do my job in this episode, which is keeping us on track. But a couple questions. What are some other examples of cratons? And do you use the word craton in your intro? Do you introduce your students to the cratonic or cratons?
That's a really good question. I'll go the second one first. And I do kind of, only because I'm talking about my research. I don't teach it in the intro level as a thing they need to know in intro geology. It's definitely second order like classes, second level classes.
Okay, and I asked that question only because today I introduced the word craton to my students because we were doing geochronology, relative dating, and I drew up a cross-section on the Algoma district in Canada, and all I did was I made statements about the rock types that I had drawn in the cross-section, and I asked my students to say whether they were probable or not probable statements.
Oh, interesting.
And one of them involved a cratonic setting, and they did not know what that was. And so I had to introduce just today, actually, what craton and cratonic meant.
So you don't often do this in class, or is this not every year? Okay. And how did the students?
No, I do this, but I don't use cratonic. Yes.
Okay. Gotcha. Yeah.
Okay. Sorry. So I interjected, but examples.
Yeah. So I refer to cratons. What I often mean when I'm talking about cratons is Archean cratons. So blocks that are older than 2.5 billion years old. And there's like 5 in North America, probably 8 in North America. And they're all kind of aggregated together to make the Canadian Shield. Another one, There's a couple in South America. There's the Sao Francisco craton, and there's a couple of them that are amalgamated together to make the interior of South America. There's a really famous one, several famous ones in Australia, a bunch in Africa. Yeah, so they're all over. They're underlying continents mostly.
Okay, and does it refer also to a specific rock type?
No, craton is a block of stable crust, and it can be made up of a whole bunch of different rocks.
Do I live in Southwest Michigan? Am I a part of the North American craton?
Yes, you would be. I mean, basically, you're part of the craton if you're sort of roughly near sea level, which is, within a kilometer of sea level, and not much has happened recently.
Yeah, that's the way I describe it to my students. When I talk about a craton, I say, look, I'm in the middle of a continent. I'm in the stable interior portion of a continent where not a lot is happening. Yeah,
that's exactly right.
So, Jesse, my second question then is, you described the Canadian Shield, which is a lot of granite, and it's a really, really old basement rocks. Describe how that forms and how that gets exposed at the surface.
So cratons, sort of by definition, they just bob right near sea level. Kind of, they're a little bit exposed above or a little bit below. North American craton's a great example of this. Like where you're in Michigan, you're sitting on sediments and it kind of bobbed up and down. Now it's above sea level. If sea level rises, it's a little bit below sea level. That's what cratons do. But the relevant point here is that cratons started forming 2.8 billion years ago, roughly. There's a whole bunch of cratons that formed and stabilized, had their final stabilization around 2.8 to 2.5 billion years ago. We don't have cratons that are older than that. We have cratons that are younger than that. The rocks at the base of the Grand Canyon.
That's interesting.
Talked about the Grand Canyon, the gneiss is that's basement, that's craton, that's North American craton exposed at the bottom of the Grand Canyon. It's 1.8 billion years old. So that's a younger craton. But we don't have anything older than 3 billion years old that would qualify as a craton. So we kind of Earth got to sort of teenage years and cratons started forming. That's kind of the question we're addressing. Like, why that time? What was going on that if we go back further than that, the rocks are different. There was less granite.
So can we tease this out a second?
Absolutely.
Can we tease this out? Like, how do we ever get rocks then that are older than this?
That's a great question. This is my opinion or take on this, is that as soon as you make silica-rich continental crust, what we think of as continental crust, rocks that are more like granite, they're not quite granite in the Archean, but they're intermediate in composition, let's say. Tonalites, andesites, that kind of composition. Those kind of float. They're less dense, so they float up a little bit. And then they kind of bop around, and they remain in the continental crust package, but they're not stable. They would get metamorphosed. So if we go back to the Acosta gneiss complex, 4 billion-year-old rocks I did my PhD on, those have been metamorphosed.
Just so everybody knows, me and a few of your other close friends used to just call you Acosta.
Yeah, that's right. You wouldn't even give me the dignity of calling me Mr. Acosta. It was just Acosta.
No, absolutely not. Just, Hey, Acosta, shut up.
Because every time I'd just be rambling on about Acosta.
It's so good.
Yeah, exactly.
All right, sorry. Go ahead. Carry on.
4 billion-year-old rocks, they're silica-rich. They're intermediate composition rocks, so they sort of float up. But they were metamorphosed 3.8 billion years ago, 3.5 billion years ago, 3.2 billion years ago, 2.9 billion years ago, 1.9 billion years ago. So they've been metamorphosed a whole bunch of times and deformed and turned into gneisses and stuff like that. So they've not been in a stable thing. They're not part of a craton. A craton is like this block of crust that nothing happens to it.
It's too buoyant that it's too far away from all this stuff.
Exactly. And it has this big keel beneath it that kind of, it provides this, it's like a buffers that don't allow tectonics to manipulate the rocks above.
You get the segue award because that was my next question. How does the continent develop this keel?
Oh, that is such a great question. We don't know. What we do know is cratons started forming, or they started being preserved because a craton is a stable block of crust. They started stabilizing 2.8 billion years ago, roughly. We don't get many samples of the keel beneath the continents. Really, the only way is these kimberlite volcanic deposits that bring up diamonds. They bring up pieces of the mantle. And they're very small. It's not a representative selection of the keel. My opinion on this, and we've done some work from ancient diamonds on this, is that it was sort of plate tectonic-like processes. That kind of thrust, if you take the oceanic crust and it's subducting, and you kind of shove it underneath of a continent, and then you break it off and you shove another layer under and you shove another layer, you can kind of stack, what's called stacking. You stack these things together and it gets thick, and then it can become cool enough to stabilize. Because you're taking cold oceanic plate and shoving it down there, and it cools down and stabilizes. That's one idea. That's not necessarily the right idea. There's a lot of debate about this. Mantle plumes could
There is
maybe
a lot
do
of debate
this.
on this? Okay.
Yeah, mantle plumes are, some people argue mantle plumes do this. But
well, you're a mantle plume guy, so.
Yeah, we talk about Yellowstone all the time.
Right. I mean, you put kids to sleep all the time.
Exactly.
What is a magma chamber?
Yeah,
so,
banging on about that.
So Jesse, can you just take, please, 30 seconds
yeah,
and tidy this up for us?
Okay.
Because then I want to move on.
So to answer the question, we do have rocks older than 3 billion years old, but those rocks were not a part of a craton. They were stable because they're buoyant, so they kept in the crust, but they got bombarded a whole bunch. They got overprinted a whole bunch, whereas a craton is something that doesn't get metamorphosed or doesn't get deformed.
Okay, Jesse, let's continue on with your paper then. What are the takeaways? Like, I don't know, I would say like, give us 3 takeaways for the purpose of this paper, or your findings, actually, I think is what I want to ask.
So could I do one 30-second framing? I think we need one more piece of information that kind of frames
that
this.
Might take me off on another rabbit hole, but okay, go ahead.
So what do you need to stabilize continental crust?
Buoyancy.
You need buoyancy, absolutely true. But what you also need is you need to get all the heat close to the surface. The thing has to be cold. You need to have a really thick and cool package of crust. And Chris, we've talked about this a bunch. Rocks have radioactive elements. When uranium, thorium, potassium decay, they release and produce heat. If you have that stuff down below, the thermal conductivity, rocks don't conduct heat. So that heat kind of gets trapped down there deep. So you have to take all the uranium, thorium, potassium and move it right near the surface. And what that means is you have to melt the crust. The best way to do that is to melt stuff deep down. All the uranium, thorium, potassium goes into the melt. The melt migrates up, maybe erupts out onto the surface as a volcano, and you have all your heat-producing elements, what we call heat-producing elements, uranium, thorium, potassium, at the surface. So all the heat, the internal heat engine is at the surface, which means it can cool off, and it can cool that whole block of crust down because there's no heat being produced down deep, or there's less heat being produced down deep. So Archean cratons have loads, like shitloads of granite at the surface. There's granite everywhere in Archean cratons because of this magmatic event that removed all the heat from the deeper parts and put it up to the top.
That's the answer to my other question from a long time ago then, right? In terms of why there's so much granite exposed in the Canadian Shield.
That is exactly why. So to frame it, people have debated what did this process? What would do all this melting? People have said mantle plumes. You put a mantle plume underneath of like a proto-continent and you melt the heck out of it. You move all that granite to the surface, you could stabilize it. A subduction zone is a great place to melt stuff. You're melting things, you're moving the uranium, thorium, potassium up near the surface, and you cool down that block of crust. So there's a bunch of different ways to do it. And so I don't know if you have other questions or you want me to sort of add some conclusions to this, but or what our sort of thesis is here. But
I mean, I do have a question, and I guess it's trying to best frame this. Why would this happen where it happens? What concentrates these radioactive elements that then rise up with the magma? And then the other thing, Jesse, is that, okay, so they melt this stuff near the surface or at the surface. That doesn't form granite then, because granite is intrusive and it's deeper, it's slower. And so those are the two questions that I mainly have.
Maybe I don't think I explained this quite well. The granite at the surface, it used to be 1 kilometer deep or 3 kilometers deep. But near surface, not 20 kilometers deep, but 3 kilometers deep. You need to mobilize the heat producing elements and get them up to the surface. The way to do that is if you have a rock deep down 30 kilometers deep in the lower crust, and let's say it's a sediment that has a bunch of uranium, thorium, potassium, how do you get that uranium, thorium, potassium up to the surface? Really, the only way is to make a melt, to melt that rock, and the magma that's formed loves uranium, thorium, potassium. What's left behind hates uranium, thorium, potassium. So the melt gets enriched in uranium, thorium, potassium, and then the melt travels, migrates up like magmas do, to the near surface area. And then all that uranium, thorium, potassium is locked up there. And when it decays over the next 3 billion years, all the heat is just lost to the atmosphere very quickly instead of being trapped in the earth.
And the important thing with that, too, is that it has a lid.
It has a lid. That's exactly right.
Yes.
Yep.
Okay.
Exactly.
That makes sense. Okay. I get you. So you set the stage. Takeaway from your research.
The takeaway here is we've proposed another model, and I think in some ways a better model, for how this could have happened. What was special about 3 to 2.8 to 2.5 billion years ago? Why did cratons start to form then? And I think we provide a perhaps better model. Like, we think mantle plumes have been happening since the beginning of Earth. So if mantle plumes are forming cratons, why did cratons only start forming 2.8 billion years ago? Why did it take that long? And what
Jesse, can I hold on? Let me interject a second. Yeah. Can you really quick give a couple examples, well-known examples of mantle plumes to paint a picture for everybody?
Sure.
What a mantle plume is.
Well-known examples of mantle plumes are Iceland. Has a mantle plume underneath of it. Also has a mid-ocean ridge, so tons of melting. Iceland's kind of a proto-continent. Hawaii is a mantle plume. Yellowstone is a mantle plume, and there's loads of melting going on in Yellowstone. So you can envision this scenario, like why this might be happening. Mantle plumes aren't necessarily a great way to form cratons, though, because they melt everything. Like, mantle plumes come up to the surface. They're huge. They like erase the root. They don't form.
And they express themselves differently on the surface.
Yeah, that's exactly right. Exactly right. So back to the question, we're trying to answer the question of what was unique about Earth 2.8 to 2.5 billion years ago where all these cratons formed in this interval. And what we did is we looked around and said, well, what else was happening on Earth at that time? And there's pretty good evidence that prior to about 3 billion years, so before 3 billion years ago, the Earth was a water world, which means the continents that were there were mostly submerged below sea level. So they were subaqueous, below sea level, not subaerial, exposed to the atmosphere. And if you look at the old rocks, the rocks that are older than 3 billion years old, they're really intermediate rocks. They're like andesites. They're not granites. They're a lot more like andesites. They're not that much granite around.
So the important part about that is they're not as buoyant.
They're not as buoyant. They're different composition. They have less uranium, thorium, potassium in them. You also don't have sediments. There's not a lot of sediment on Earth prior to 3 billion years ago, like those old rock terrains.
So why would there not be sediment if you had a water world?
Exactly. So that is a great question. I hope the listener is thinking about that a minute. Why would you not produce sediment? What do you need to produce sediment? Well, you need rock above sea level. Erosion isn't happening below sea level. You're not breaking minerals down. I mean, a little bit you are, but weathering under the ocean is just you form a little weathering rind on the rock. You don't actually break down rock and remove it with rivers or glaciers and put it out in the ocean, and then you have fresh rock exposed. So weathering and erosion is very much a process that happens when rocks are exposed to the atmosphere, not just to the ocean. So if continents are submerged below sea level, you don't form a lot of sediments. There are some sediments. Like, you can imagine if all the continents are below sea level, if you raise sea level a kilometer, a lot of the continents are going to be underneath the water. What's going to poke above? It's going to be active volcanoes. Japan. Volcanoes poke up and then they get eroded down really quickly. That's not a huge volume of stuff. You produce lots of sediment.
Yeah, it can be localized. Yep.
Very
absolutely.
localized. And that did happen, but you didn't have like Mississippi River type drainage, Amazon, Nile River, weathering continents. So what we said is we made that observation and we said, okay, maybe this is important for melting the continents. What happens if you try and melt continents without sediments versus what happens if you try and melt continents with sediments? And it's a dramatic difference, especially when you go back in time, because 2.5 billion years ago, there was a lot more uranium, a lot more thorium, a lot more potassium than there is today. So the heat blanket, the radioactive heating was a lot higher. So sediments have a ton of radioactive elements in them. They're really good at concentrating uranium, thorium, potassium, especially shales. So what we propose is continents raise above sea level, for some reason. They start to form sediments. Those sediments get thrust down deep in the earth, and they start to melt the continents because you've got all this radioactivity 30 kilometers deep, which melts everything. And that's a good way to form a thick, stable cratonic block of crust.
How did the sediments get thrust down 30 kilometers?
You would have to have something like plate tectonics to do that. Okay. And in my
Subduction,
opinion, not everybody
like that, right?
agrees with this, but my opinion is we have great evidence for subduction back then. So to me, that is an easy one. Like, we think subduction was going on then. So you just add sediments to a subduction zone system, and the sediments go down. They get pushed deep underneath of the crust there. Yeah. And then they melt that crust.
That is now, I think for everybody, my mom is undoubtedly asleep right now. However,
yeah. This title, is a good nap episode for Joyce. Yep.
But the title now makes complete sense. And I think to people that have been tracking, it does. It makes complete sense now that subaerial weathering drove the stabilization of the continents, because we had these sediments that were being driven down in subduction zones, rich in these radioactive elements, and causing melting that took place.
Exactly. And so, if you'd allow me, Chris, am I allowed to say two little things here?
Keep it tight.
Okay, keep it tight. So thing number one is that this process would be more important back in time because there's more radioactivity back in time. Sediments today, they have less uranium, thorium, potassium because a lot of it's decayed away compared to 3 billion years ago. So this process would be a more powerful process back in time. So it would explain why cratons formed 3 to 2.5 billion years ago, but they aren't really forming that much now, or they're not forming by this process today. There's a big difference between Earth as a teenager and Earth today because of radioactivity. And the second point I want to make is that this paper, well, my postdoc supervisor, Rick Carlson, who's a very, very highly regarded scientist in the early Earth planetary science community, really top flight scientist, he always described Nature papers as the best Nature paper was a good idea that might even be right. Which, it means it's like one of those interesting ideas, but it's certainly unproven, and, it could be wrong. And I would put this paper that we've written is very much in that category. Like, it's a new idea. There's a little bit of evidence. There's like hints of evidence backing this up, but it certainly needs to be tested. We have to go out and test this. It's provocative, but not untested. It's a good story. It makes sense now, but we need to go test it. Kind of like Mike Ackerson. We talked about Mike Ackerson's Nature paper on granite formation. It's the same as that. There's good evidence for this proposal, but we really need to go test it more.
Are you going to present this at GSA or AGU? Or?
Yeah, I think Andy Smyth, my co-author, he's going to present it at the Goldschmidt Conference, which is the geochemistry conference, and the other conferences are not till the fall. So we'll be presenting this around at conferences for sure. Just because it's something that we think needs to be tested by a bunch of people, a bunch of different lab groups, not just us, other people.
So would you be nervous standing up in front of a group of scientists, your peers, and presenting this research?
I gave about 75% of this talk, of this idea at a conference about a year and a half ago. I was very nervous. It was
It's always a nerve-wracking thing anyway.
Especially when it's something that's new, that hasn't been like reviewed, and you don't know what the response is going to be. I would say I had a couple nice comments. A couple people said that's really interesting, really cool. And then a couple people were like, yeah, in my part of Australia or Canada, I don't think there's good evidence for that. So, you haven't considered some things, which is good. Like that, that's the conversation you kind of want to have. So,
yeah, I've seen these things go sideways, so that's why I've asked.
Yeah, no, exactly.
So, Jesse, maybe we're ready to wrap this up, but I want to ask one final question.
Quick.
Maybe. Yeah, I know.
No, I'm kidding.
I know.
I'm kidding.
I guess I want to know where this idea came from.
Oh, this is good. It came from a conversation over a couple beers in my living room. Really, it was just
really? With who?
With Andy.
Was it
Smyth.
with Andy?
With Andy Smyth, yeah.
Really?
And another colleague, and we were just kind of talking shop, talking about research. How's your research going? What are you thinking about? This kind of thing. And so it's really fun that way, because it's just a conversation with colleagues that ends up, you kind of have these conversations. It's like you and I, Chris, when we were talking about we were circling like the Camp Geo thing, making audiobooks with images. We didn't come up with that idea out of thin air. We talked about a problem for a long time. We kind of went back and forth. You wanted to do a course in the podcast. You wanted this podcast to be like a course. I didn't really want that. We went back and forth. Then we're like, we need images. Maybe we don't need images. How do we make it work? And then it kind of hit. We're like, wait, we need to build an app for this. Like, it was very much like that. Very casual conversation. We were just kind of batting around ideas. And then somebody says something. And you're like, oh, wait, that might be interesting.
That is interesting.
And
How
that
long
happens
was
a
this
lot.
process then?
What's that?
How long was this process?
Oh, boy. Probably about 2 years, year and a half, 2 years. It just takes a while. But you know what? These ideas, sometimes those ideas happen, and then you go and you you look at the literature and it's like, oh, wait, somebody did that in the 80s. It was a good idea. I just didn't know somebody had already done it or whatever. Or maybe you realize, wait, that was a terrible idea, and here's why. But this one, it kind of was like, no, wait, this might be a good idea. And we kept going deeper and deeper. And so, but like I said, it could be wrong. And I think, I was excited to do this as a podcast episode in large part because I love talking about this. But I also think it's a good way to introduce the early Earth. I think it's something that many people don't know. Even really good practicing geologists don't really have a full grasp of how different the early Earth was compared to our modern planet and how little we know about the early Earth. Like, we don't know what was going on 2.8 billion years ago, which is Earth was a teenager. Like, we didn't understand that. It's kind of crazy, right? So
yeah,
that
is
was exciting
because we
to me.
throw around big numbers all the time.
Yeah.
And sometimes we get into a little funk with that. We maybe throw them around a little too flippantly.
That's right.
Like we really
I agree.
do know what was going on. And
that's a really good word, flippantly. That's a good way to describe it, for sure. For sure. Cool.
All right, what's next?
Well, we're going to go test this. What we need to do is, one of the beauties of this paper, one thing I'm really excited about, is that it's really good science in that it's a hypothesis that outlines how it should be tested. And if this model is true, there should be a bunch of sediment preserved in the roots of cratons. And so we need to go look for that. And there's very specific predictions that you can make based on what those should look like now, because the model suggests how they would form. So we're going to go look for those. We're going to go, hopefully we're going to write some proposals to kind of have students funded to go do work in South Africa and up in Canada and look at the minerals in detail. And so, yeah.
So the most interesting thing you said this whole episode is that last sentence about we're going to go look. There should be sediments buried in the cratons. That's really interesting.
That's one outcome. If this model is accurate at all, that they should be there. That's what this model
when does
predicts.
this start then? When are you going to look?
Well, we've done some literature review at the moment to kind of see what rocks do we know of. We're going to write a proposal that is going to go in South Africa in the what's called the Kapval Craton. There's a big meteorite impact, the Vredefort impact structure. Meteorite impact hit, huge impact, and it tilted the crust. So basically we have, there's a tilted crustal section.
So you have exposed rock then.
Exactly. There is exposed crust from deep, 30-kilometer deep crust gets brought up to the surface, but you don't know how biased that is. Was that just a really squishy bit that got brought up? In the Alps, there's some lower crust that's been exposed. This is a meteorite impact and it just tilted it. So you're getting like an unfiltered view, unbiased view of the Archean lower crustal package. So we go look for sediments in that package, which will be fun.
Really cool.
Yeah.
Yeah. No
so
kidding.
hopefully, so if anybody from NSF is listening, you should fund this proposal.
Time frame?
Ideally, the shortest it would be is submit the proposal here in a couple months. Hear back in 6 months that it's funded, try and go next summer, next fall, maybe to go do some
so a year and a half.
Yeah, year and a half before we even get started. And that would be collecting the samples. And this is probably PhD project level. So results coming online 2 or 3 years from now kind of thing. So, but hopefully there will be other people who have these rocks in hand who read our paper and say, wait, I can test that with my rocks I have in the lab. Let me go look. That would be a quicker way to do it. We kind of have to go chase funding, which takes a lot longer. But,
very interesting, Dr. Reimink.
Well,
I called you doctor.
Thanks for supporting me.
I ripped on you in my class today. So.
Oh, yeah? What'd you say?
Yeah. I just talked about how you like to be called doctor.
Oh, yeah.
And how I don't like to call you doctor. And then I'm like, he doesn't really deserve it. And So,
that's true. Did you tell them that you like to be called doctor by some of our listeners?
No,
you didn't say that.
I did not. I didn't say that. No, I'm not gonna do that.
Well, when I zoom in with your class sometime soon, I'll tell them that you like to be called doctor too every once in a while.
Okay. All right.
Oh shoot. All right.
That's
hey.
fair.
Well, thanks, Chris. Thanks for humoring me. This was a fun episode for me. I hope it was fun for you, and I hope it was fun for the listener. You can find out more about us. Go to planetgeocast.com. You can support us. There's 2 ways to support us, and we appreciate both of them. Go to planetgeocast.com. There's a support us link there to help us, keep the show on the road. You can also go to the first link in our show notes, which is the Camp Geo app. You can download our mobile app. You can listen to a whole bunch of content regarding basically the intro to geosciences, the Camp Geo content. We also have several audiobooks for sale as well there that you can buy, visual audiobooks. So listen to Chris and I talk about Yellowstone or the Grand Canyons with all the images you need to learn really deeply. So head there. If you have any questions, send us an email, planetgeocast@gmail.com.
Cheers.
Peace.